like this one. Okay. So this is called STM microcontroller. It's a very popular company in the industry. A lot of people are using that. Let you guys know, one student graduated not even from the C program. He graduated from the engineering program and took the digital systems concentration. I believe some of you are in that concentration. So just in his junior and senior years, he took microcontrollers, took robotics, took digital signal processing, all those courses, and he was able to develop a system in my senior seminar design project and got a job in Stone Age, which is an embedded system company in Durango. Even though probably the payment won't be as high as a similar job in Silicon Valley, but it's comfortable, I think. So also you can expect a job like that if you want to stay in Durango. Okay, Stone Age and Soundtracks, sometimes they're hiring embedded software developers, but who has to be able to make PCBs and build a whole system. So that's why this is super important. You'll get a chance to make at least one or two PCBs in this class and another one or two PCBs in your senior seminar design. So eventually you'll be really good at it in order to get a job, secure a job. So why is it more popular than this guy? I mean, similar memory, similar functionality, similar capacity, but the thing is, this is only like $1 or $2. It's like $17. So cost is very important in industry. So I think maybe the next version we can consider another platform using the STM. Eventually we'll go with this one instead of Arduinos. But the good part of the Arduino is there's so many examples online, so you got a good support from the society. I think that's the strength of using Arduinos. Okay. This one has 100 pins. You see really dense pins around it. Doesn't like the Arduino Uno's pins. There's only 28 pins. It's called DIP, D-I-P. It's like a dipping, right? So when you plug into the board, it's dipping. So the DIP package, it's a 28 DIP package. This is super simple to solder because you can directly just put a socket on the PCB and solder from the back. But for this one, first it's a surface mount soldering. Second, it has super dense pins. It's 100 pins. It's 25 on each side. For the first time student, like you're soldering this board, it could be challenging. However, you have to get into this sooner or later, okay? Because during the interviews, they'll ask you these questions. Have you soldered a board with surface mount components? They'll ask you these questions. So you want to tell them you have done that, and also you have done that multiple times, okay? So there are different packages that you need to be super familiar with. Like all these resistors and capacitors, you can see they are not, compared to my fingers, they are not too small, okay? Not too small, not too big at all. So these are the comfortable sizes we want to use. It's called 1206. So it's 0.12 inches by 0.06 inches by size. There are also popular packages called 0805 or maybe just 0605, 0805 or 0603. So it's going to be 0.06 or 0.03 inches. That will be the smallest one I can use my fingers, which is 0603. That's the one I've been using for a long time. But I figured that students couldn't do it. So I stopped using that one. And what about 0805? It's slightly bigger than 0603, but still not perfect. I think 1206 is the best one for students to solder. So that's why we started using 1206 for all the design, starting from this board. And you'll see some of the packages are still small. It's because we just couldn't find the 1206 package for that certain chip. So we have to use the 0603 or something else for it. So eventually for the final project, what you are going to expect is going to be a PCB design. Instead of just soldering, you are going to design your own PCB. So you have to learn how to use that PCB software. It's called the EDA in Fusion 360. It used to be called Eagle, but Eagle will be discontinued next year probably. So we cannot keep using Eagle even though I like it a lot. We have to switch to Fusion 360. It's a very similar environment, just the core is still Eagle, just a newer interface. So you have to use the same chip and add either the sensors we have been using for the whole semester on this board, or you can add new sensors, new display modules to your design, and make your own PCB, fabricate it with GLC PCB, and receive it and solder it and test it. So that's a whole the course project you can expect towards the end of the semester. Okay, so the outcome of this course is so you guys, all of you guys, will be professionals on PCB design. It's not just a simple PCB design, not just a simple analog PCB design, but it's a system level. Okay, so you got the microcontroller and oscillator to drive it, and also you program it and interface with the peripherals. So that's a goal. Okay, so you can put a lot of things on a resume after this class. Believe me. All right. So in-class exercise is part of the grading. So homework assignments, in-class exercise, and quizzes, 50% of the grade. So now I want to start with fundamentals of some of the logic stuff that you guys probably already forgot, but I will run it really quick. First, if you want to understand sine and unsigned numbers, you need to know what the 2's complement is, right? Do you still remember what a 2's complement is? So what is 1000 as a signed number? Okay, so it's necessary to run this. What is 1? What is 10 in 2's complement though? 10. 10 is what? -2, right? Okay. What is 01 in 2's complement? Still 1. Okay. So the thing is, when we want to represent negative numbers in the computer system, there's no place to put a sign in it. You know, what is a sign? The circuits can only hold voltages, right? So 0 and 1. So 1 is, for example, 5 volts for VDD. So that's going to be 1, right? And GND, which is ground, will be 0 volts, right? So that will be 0. Okay. And the transistors, that's why you need to learn transistors, because transistors are able to hold all these values and giving you all these logic numbers, and so you can do all this computation in the computer, right? So these are basically just the voltages, voltage levels. If the 5 volts logic, the VDD is 5 volts, you are getting 5 volts logic. So 5 volts represents 1, logic 1 in the computer system. If it's 1.8 volts for the VDD, you are getting 1.8 as a 1. In your logic 1 in your computer system, but the ground or 0 volts is always 0 in your system. Okay, this is not being changed. So the thing is, why we want to use 5 volts lower voltage instead of 5 volts always? 5 volts is a really old technology, probably 40, 50 years old, right? Like the Arduinos, like these ones. So these ones are being fabricated in 350 nanometer technology. Okay, 70 cents is so cheap. We're still using it. Okay. So it's using 5 volts. It's 5 volts everywhere. It's 5 volts on the chip, 5 volts in the core. So using lower voltages can lower the power consumption. It's a very significant change to that. So we want to switch it to like 1.8 volts, even 1 volts. I think for the 3 nanometer technology is probably, I don't know. I don't want to give you incorrect information, but I think it's lower than 1 volts. Okay. So in that case, we only have numbers, right? We don't have numbers. How do we represent negative numbers in the computer system? So people have been thinking about adding a 1 in front of it. So if you have the most significant bit, MSB, to be 1 something, then we treat it as a negative number. But is this the negative number physically? No, it's just a 1. It's just a 5 volts being held by the transistor. There's no difference. We just treat it as a negative number because in the computer system, when you take out the numbers, you already told the computer, hey, this is a sign. Don't use that as a number. Okay, but physically it's a number. Okay. So in that case, if we are treating this one as a sign, then we are wasting 1 bit. So people are thinking, why not just treating this as a sign and a number as well? Okay. So whenever you got a 1 here, it's a negative number, but also this one represents something. So eventually we got into a conclusion that we can use this one as, so in a positive number system, unsigned number, this is 8, right? So in 2's complement, we just treat it as negative 8. That's it. However, when we are doing the calculation, in theory, we are flipping. Let me see how we do that. So like a positive number like this. This is the positive number, okay? So if you want to convert it to its negative counterpart, we are flipping every single bit. So we're getting 1 0 1 0, right? And we're adding a 1 to it. So it becomes 1 0 1 1. So as a positive number, this is 5. Okay. As a negative number here, how do we calculate it? Because I told you this is negative 8. It's not 8. It's negative 8. So it's negative 8 plus 0 plus 2 plus 1. So this gives you negative 5. So in theory, for 2's complement, to find the negative counterpart of the positive number is that you have to flip every single bit and add a 1 to it. That's called 2's complement. So before 2's complement, people use the 1's complement, which is just simply flipping every single bit and treat it as negative 5. But we find out it's not as good as this one for a lot of reasons. So eventually we flip it and then add a 1 and we treat this thing as negative 5. And the way to calculate it is we treat the MSB as a negative of the physical MSB number. That's how that works. Okay. So this is a signed 4-bit number. It's a signed 4-bit number because the MSB represents a negative number, so that's why it's a signed 4-bit number. All right. So today we are not getting into the in-class exercise. It's going to be next. It's going to be Wednesday. We'll start working on that next Wednesday. So what I'm covering right now will be the materials in homework 1. Okay. So I can write. So the format of binary number in your C program. A binary number can be written as 0B 1010. Got to add a prefix here, 0B. That's a binary number. It's a lot of times when we are programming hardware, you want to split all the bits and show all the digits in the bits because it's different from the C++, a way higher level programming language on the keyboard. You want to visualize all the bits because all the bits are controlling the pins. Like for example, you toggle the blinked LEDs, right? You drive a motor or something. That pin, like this pin, is directly controlling like pin 10 or pin 2 like that. So you really want to know all the bits. You want to display all the bits. That's why we have a lot of times we use this format, 0B 1010. We know we're declaring a exactly 4-bit binary number here. So what about 0x? That's a hexadecimal number, right? as a hex number. So how many binary bits in here is this hex number?
16.
No, I mean just for these two digits, these two hex digits. So F is 15, right? So you need how many digits, binary digits, to represent 15? It's just 4 ones. So convert this to binary number. It's basically 1111, 1111. So you have to be very familiar with all these hex numbers in when you are programming hardware. Okay. Like FE, for example. So you know this is 14, right? So you have the LSB become 0. So this is 1111, 1110. Right? So this will shorten your writing, your typing, but still give you all the digits that you can directly interface with the pins.
Where are you getting the 13 and 14 from? You said like the F is represented by 14 and E is represented by...
No, this is 15. This is 14.
Yeah, where are you getting that from?
Okay, so this is a binary number when you count it. So for when you're counting and convert it to hex, right? So up to for binary, for decimal to hex conversion, right? For example, decimal, you have 0, 1 until 9. Okay. For hex, and then 10, 11, like that. Okay. So for hex is 0, 1 to 9. You have up to 15, but the thing is, what are the symbols you want to use for the numbers after 9, right? Like 10. You just need a 1 digit. So it has to be A. So we use A to represent 10 in hex. Okay. So then B for 11, and 12, 13, 14, 15. And this becomes C, D, E, F. Do you have 16 hex? No, right? So the maximum number in hex is F. Then F will be 15. So 15 binary will be 4 ones, right? And 14, which is E in hex, will be 1110 in binary. Good question, thanks. Mm-hmm. Am I losing anybody? All right. So on the homework assignment, homework 1, you can see the due dates on Canvas. I'm sorry for all these assignments created on Sunday. So for a binary number, I'll just write down some of the cells in the table. Okay. 0B, 1010, and I'll let you guys tell me the results. For hex, think about this one. Now it becomes a good reference. So what is this binary number? 10. Oh, I should let you know it's a signed or unsigned. Let's take the easier one first, unsigned. So 1 is not a sign, okay? So what is this number? 10, right? It's the A plus 2. Can you still recall that? How many of you can recall that? Okay, right. 10, right? 10. And hex will be 0xa, right? Okay? I'm just talking about in the C language. If you just put A in your C, it's like a variable, right? So 0xa will be a number, okay? And decimal, 10. Okay? If I do signed, minus 6, still 4 bits. We're not changing the number of bits. Zero be what? What you have in the toolbox for the digits, what you have in the toolbox, you have -8. You have 4, you have 2, you have 1. How can you mix all the things to make a -6 for you?
The 2's complement.
Yes, 2's complement. So you need a -8 first, right? So -8 plus what? Okay. What's the hex number? It's not changing. It's not a hex number. So the hex number is just a representation of the binary number here. It's not changing any other properties. If it's showing this, you just have to put an A here. So since you created that variable, you told the C programmer it's a signed number, so you can recognize it. Don't worry about that. So let's do one more practice, and we'll move to the next example. Okay. And it's signed.
12 decimal.
Signed.
Oh, it's not.
So write down this first. What you have in the toolbox?
100.
So what's the decimal number of the signed number 1100? -4, right? Okay. So for ASCII code, we'll use that a lot. ASCII code, I put a table here on my website. You can directly, as a reference, you can look at it. Oh, no, this one. This one. Right, because all the communication, when you are doing the Arduino to computer, send it to the serial monitor, is actually sending a byte to it. If you are, for example, you are sending like a character A, lowercase a, okay? So there's no way that you can send an A. It's all digital numbers, right? So there must be a digital number representation to that A. So that's why we need ASCII code. So for lowercase a, could you find me the ASCII code, a byte? So I want you guys tell me it's 0x what?
6-1.
Yeah. Yeah, here, right? Yeah. So 0x61. If you receive it as a decimal number, you are getting 97, right? Depending on how you define it, okay? You want to receive it as a ASCII code or a decimal number, okay? So that's how you can find that, and there's a trick I'm going to introduce on Wednesday for that programming part of the ASCII code. But now let's come back to the homework. Okay, the second one is pretty simple. You don't have a copy since I don't have that many papers to print everything out before the class. But you will have a digital copy on the website on Canvas, I think. So I'm going to write down the questions on the paper for you guys here. Okay, overflow. It's another thing you need to know. Overflow. 2's complement overflow. Overflow is not just simply carry out. It's not carry out, keep in mind. Sometimes you see a carry out, you say it's overflowing. No, in hardware design, it's not. They are not the same. So overflow is just specific to 2's complement. So for example, if you see a number like this, so keep in mind, overflow only happens for a positive number plus a positive number, and then you end up with the negative number, or you have a negative number adding to a negative number, you are getting a positive number. And you are thinking, why is that possible, right? It's all because we are using 2's complements. These numbers are not real numbers. We faked it. So that's why eventually you are seeing errors. And then we have to deal with that. So that's where this comes from. So let me give you an example. 111, 100, getting 2's complement. So both are negative numbers, right? So what is this one? -1. What is this one? -4. Okay? So I'm talking about, okay, 2 negative numbers adding together, you're getting a positive number. I'm talking about only the highest bit here, not including the carry out. So you see this one is 1, 1, and you got to carry out, and it becomes 0, right? So I'm only looking at this number to check if it's a p or n, okay? So 0 is p, right? It's positive. How could that happen? Negative number plus negative number giving you a positive number. Yeah, I mean, for this example, it's easy. You just adopt the carry out, right? But there are some examples you have to make a judgment. So this is the easy. But for here, if you have a negative number plus a negative number, you're looking at the highest bit, not including the carry out. If this becomes a positive number, and then you have to adopt, you have to use that carry out. You have to use it or adopt it. You have to adopt the carry out to make it correct. Let's see, this is minus 1 plus minus 4 is minus 5, right? And this is minus a plus 3 is also minus 5. So this is correct. As it becomes correct. All right? Let me see if there are better examples. What about 0, 1, 1 plus 0, 1, 1? 0, 1, 1. Okay? So this is the p plus p. You are getting an n here. What should you do? Oh, still easy.
Out of 0.
Yeah, out of 0. Yeah. So this is 3, 3. You are expecting a 6, right? Okay. But the thing is, now you are getting a negative number, which is giving you negative 2. So how to deal with that? Add a 0 in front of it. So what's the principle here? Are you adding a 0? If we keep it consistent, you are actually adopting the carry out. Again, why is that is important? Because when you are dealing with Verilog on hardware design, you have to keep it consistent, right? So you're not adding something, you're actually adopting the carry out. The carry out is 0, there's no carry out. So you are actually adopting that carry out. So keep in mind, the conclusion here is whenever you have an overflow, so what defines the overflow? This defines the overflow, okay? PP, you got an N, you got a P. These are overflows. And if there's overflow, you adopt carry out. That's it. That's simple. Just remember that, okay? Let me give you another example. 1, 1, 1 plus 0, 1, 1. What about that? First, is it possible there's an overflow occurs? No, it's a N plus P. I told you, it's PPN or NNP. But this is like a NP, right? N plus P. So there won't be any overflow. No overflow occurs. Okay? But the thing is how we want to deal with it. Let's see. This is 0, this is 1. This is 0. And there's the carry out. What should we do with the carry out? This is a good example, actually. 0, 1.
We should adopt it. Right?
1?
Yeah, 1.
So let's see. This is minus 1. This is plus 3.
Oh, it's supposed to,
And you are supposed to get a 2, right?
Yeah.
Is this 2? No, it's negative. It's negative. So introducing 2's complement is getting you errors. So we have to design the computer system to deal with it. Now, we cannot use C2, okay? I want to keep it consistent because the hardware is not that smart. Modern AI hardware are smart, but these ones are not. IPGAs are not. These are just logic gates. So what should we do for this case? So we just duplicate this guy, okay? Don't use that one. Just duplicate and put it. Duplicate MSB here and put it here, okay? It will always be correct. That's what you should do. So you are getting 0, 0, 1, 0. It's not changing the result. Okay? It's not changing the result. No matter what, no matter you have a 0 in front of it or 1 in front of it, and you duplicate MSB and put it in front of it, it's not changing the result. Remember? Let me show you. 1, 1, 0. What is this? Or let's start with the smaller one. 1, 0. What is this in 2's complement? -2, okay? If I'm adding a 1 in front of it, what's this? It's not changing. So it becomes -5, -4 plus 2 is still -4, -2. Add a 1 more in here, okay? A million ones here, not changing, okay? What about this? 1, 1, what is this? Yeah, a million ones, not changing. So adding, duplicating the MSB and putting in front of it, it's not changing the number. Okay, let alone zeros. It's not changing the number by adding 0 in front of it. No, okay. So it's not changing the number. So it's always safe to add it to this. So why we are trying to add 1 more bit in front of it? Because all the results, you have 3 bits adding to 3 bits, and the results are always, for most of them are the maximum number for a possible number of the results will be 4 bits, right? So we need the 4 bits for the space for the result. That is why I want to keep it consistent. You know, even though for the number itself it doesn't make sense, but for the computer system, we need 1 more transistor to hold that value in front of it. We need the hardware in there to hold it, and that's why we need it. Okay, we need the 4 bits for the result. Okay. More examples. For these operators, you have learned in C++. For here, it's hardware-oriented programming. Some of them can be different. For example, what is this?
And reference.
It's a bitwise AND. Bitwise AND means if you have a number here and a number like this, and you are doing an AND logic, they are doing bit by bit. So it's giving you what? 1, 0, 0, 0. That's the difference between hardware and software, okay? That's a bitwise AND. For this one, it's an event-based AND. Like a true or false, right? And true will be true. True and false will be false. Something like that. Similar to OR, so this is a bitwise OR. It's not an L, it's the vertical bar on the right-hand side of the keyboard. And this is event OR. Have 1 more minute. And this is bitwise NOT. And this is logic NOT. Actually, I should do logic OR here. It's more common.
What is the difference between those two?
These are the same. Logic event-based, logic-based, and
Bitwise and logic.
bitwise and event-based. Event-based is just the event, just like true and false, right? True or false will be true, right? So that's just the one logic. It's a logic. It's not a number, specific number. For bitwise, it's multiple numbers in a row, and do bit by bit and or logic. It becomes really handy on hardware because a lot of times we want to do signal processing with pins at the same time. So we have sometimes we have 16 bits being AND or ORed to another 16 bit at the same time. So it's doing that really quickly. One line of code can get everything done. Okay. See most of you on Wednesday to work on more of the problem on the in-class exercise or the home assignment. Okay. Is there a quiz on Wednesday?
Yes.
Is that Friday or? Oh, it's Friday. On numbers. Okay, we'll cover more on numbers on Wednesday, and we'll take the quiz on Friday.